This is Group 2, and we decided to do navigation for our second presentation. We chose it because navigation is something that people use every day, but they don't know that math is behind many of the navigation services that are used. If people don't know of the math behind navigation and navigation services, they won't know of the discrete math behind them either. We're going to start out by going through the history of navigation. This will include tools and theories. This is important because although the technology has changed, a fundamental point has always stayed the same. We will talk about the evolution of navigation after the adoption of computerization, and we will talk about how navigation is used today and demonstrate it with discrete math. Finally, we will talk about the discrete mathematics of navigation. This is mainly graph theory. History before the invention of the compass. So, the compass is one of the more recognizable forms of navigation tools. It has also been around for more than 2,000 years. But what did people do before the invention of it? Well, they did all sorts of things. The most basic process that was used was the sighting of landmarks, sometimes supplemented with the sighting of the positions of the stars. This was one of the more common ways to get around. There are also a few other unusual or ingenious ones, like a technique in China that used mud from the seafloor. I'm not sure why or how this was done. A few ingenious techniques were used in a variety of civilizations, such as analyzing the flight pattern of birds, observing wind in its direction, and observing sea debris. Invention of the compass. The compass was invented in China during the Han Dynasty. It was originally called the South Governor, or South Pointing Fish. At first, the compass wasn't used for navigation. They were mainly used for geomancy and fortune-telling. Geomancy is a method of divination that interprets markings on the ground or patterns formed by dirt, rocks, or sand that have been thrown. The early compasses were made of lodestone, a naturally magnetized piece of the mineral magnetite. Lodestone aligns itself with the Earth's magnetic field. When the lodestone was suspended in a way that it could turn freely, it would always point towards the magnetic poles. These early compasses were used to find areas suited for houses, fields for crops, and the search for rare gems. The compass was only adopted for navigation some 600 years later than the Han Dynasty. Early navigational compasses. The typical navigational compass in China was a magnetic needle floating in water. This is known as a wet compass. There was also a non-water compass known as a dry compass. It was suspended upside down in a wood frame made in the shape of a turtle. The lodestone was sealed by wax. When rotated, the needle at the tail would point in the cardinal direction, which was north. Different types of compasses. A bearing compass is a magnetic compass that is made in a way that it allows the user to take bearings of objects. A bearing is the horizontal angle between the direction of an object and another object, or between it and that of true north. A liquid compass, not to be confused by a wet compass, is a design that has the magnetized needle damped by fluid in order to prevent excessive needle swing, while improving readability. These types of compasses were meant for ships. Other tools used in navigation. Astrolabe. An astrolabe is an ancient astronomical instrument that was designed to look like a model of the universe. It fulfilled a variety of tasks, like measuring altitude, identifying planets, and surveying. The surveying is the most important part. This technology was changed to be used on ships. This new technology was known as the mariner's astrolabe. This tool was used to determine the latitude of a ship at sea by measuring the altitude of the sun at noon. Of course, the sun wasn't the only star that was used. The mariner's astrolabe was a much simpler model of the astrolabe. It was made out of brass because the extra weight would be helpful on a moving ship or windy day. As shown in the image, it was used by holding the tool from the top. This made the instrument remain vertical. The user would then align the middle part to the direction of the object being used as a fixed point. The middle part would then align to the object and an altitude on the circle. This tool was very limited. Because the astrolabe had to be kept vertical, in windy conditions it was unusable. It could not accurately find the angle between two objects, and that was an important part of finding longitude. Some more navigational tools. The sextant. This was a solution to the astrolabe not being able to accurately measure the angles between objects. This tool allowed the user to measure the distance of the fixed object relative to the horizon, rather than the distance from the object to the tool. The sextant also allowed for the direct observation of stars. This allowed it to be used at night when other navigational tools were harder to use. When it was used during the day, a filter could be applied to not blind the users. Since the measurement was based on the horizon, any accuracy issues were based on angular accuracy of the instrument and not the errors like different navigational tools. The sextant did not require steady aim because it measures a relative angle. This allows it to be used during a windy or stormy day. Something interesting that I found was because the sextant doesn't rely on electricity, it's still used today as a practical navigational backup for ships. Many of the early navigational technologies relied on a fixed point for help in navigation. This fixed point could be anything from a landmark to the stars in the sky. Although the technology has changed a lot since then, many of the navigational forms we use today still rely on using a fixed point. Now, we will talk about how navigational tools changed thanks to electricity and computers.
Now I'm going to take over and talk about the history of computerized navigation. I'm going to start by talking about how radar came about, then talk about how it was replaced by GPS. Radar, which stands for Radio Detection and Ranging, is a tool that makes use of radio waves to tell you information about your surrounding. Bounce off various objects, and the strength at which they return tells you how far they traveled and what they bounced off of. So, how was radar discovered? The answer is, you guessed it, war. The story starts in the late 1800s with someone called Heinrich Hertz. He conducted an experiment that conclusively proved that electromagnetic waves exist. Before his experiment, visible light was the only section of the electromagnetic spectrum, a fancy phrase for all kinds of energy waves. That's about as far as he got. His research would later be picked up in the middle of World War II. During World War II, it was important to find airplanes and submarines of the opposing forces before they attacked your city. The problem was, no one had a reliable way to see threats until it was too late. It's hard to see planes behind clouds, let alone at night, and the deeper a submarine, the more invincible to the naked eye. We read a lot about the early radar system that was in operation at Pearl Harbor in December 1941, when the surprise attack by Japanese naval airplanes decimated the fleet with a 3-hour-long raid beginning around 8 on that sleepy Sunday morning. They needed a solution, something that could look right through the clouds and water and darkness as if they weren't there. Sir Robert Watson Watt is often recognized as the person who found that solution. In 1935, he began experimenting on whether radio waves from airplanes could be detected. He then won a patent and went on to create the Chain Home Network, one of the first early warning radar systems in the world. The Chain Home Network was a series of radar transmitters and dishes that would flood the area with radar signals. After the Chain Home Network, lots of other types of radar began popping up during World War II. The US had their LORAN, which stands for Long Range Navigation, which helped the world. In Germany, the Würzburg radar was detailed enough to distinguish British and German planes. Even after the war, these technological marvels didn't just fade away. The LORAN isn't used much today and has been mostly replaced by the GPS. The first image you have at the top is the LORAN, and at the bottom of the page we have Germany's Würzburg radar. Now let's talk about GPS. GPS, which stands for Global Positioning System, is a technology that involves navigation and telecommunications. GPS history is based partly on similar ground-based radio navigation systems such as LORAN. Today, it is hard to imagine a world without it. So, how did GPS come about? In 1957, Russia launched Sputnik, the first satellite to successfully orbit the Earth. As Sputnik circled the Earth, the satellite emitted a radio signal. A group of scientists in the Applied Physics Lab at Johns Hopkins University observed a strange phenomenon. The frequency of radio waves transmitted by Sputnik increased as the satellite approached, and the signal frequency decreased as it moved away. This shift is known in physics as the Doppler effect. They later expanded this idea. The Department of Defense, or DoD, wanted to ensure a robust, stable satellite navigation system would be available. Embracing previous ideas from Navy scientists, the DoD decided to use satellite to support their proposed navigation system. They launched the first navigation system with timing and ranging Navstar satellite in 1978. The satellite system became fully operational in 1993. These 24 main GPS satellites orbit the Earth every 12 hours, sending a synchronized signal from each individual satellite. Because the satellites are moving in different directions, a user on the ground receives the signals at slightly different times. When at least 4 satellites get in touch with the receiver can calculate where the user is, often to a precision of just a few feet for civilian use. GPS signals used to be degraded for civilian use, meaning that they were only precise in a military application. In 2000, however, President Bill Clinton authorized the switch off of this selective availability. Today, GPS is a multi-use, space-based radio navigation system owned by the United States government and operated by the United States Air Force to meet national defense, homeland security, civil, commercial, and scientific needs. These days, many people take the Global Positioning System device for granted. Most people are familiar with the concept of using a GPS system to find one's way around, but there are other uses as well. GPS can also be used for tracking, such as adding a tag to an animal to see the extent of its territory. The technology also assists with mapping, such as helping to better define the outline of a country. There are likely thousands of applications for GPS systems, ranging from everything to helping hikers navigate in remote areas, to assisting farmers with precisely seeding their fields, to assisting drones with finding their targets. Now I'm going to pass it on so you can learn about graph theory.
Now I will explain graph theory. Graphs are fundamental objects in discrete mathematics that model relationships between pairs of objects. Graph theory is an important role in computer science. The field of graph theory seeks to understand the properties of graphs. Facts about graphs are useful in computer science because they help in designing efficient algorithms that operate on graphs. Graphs provide a convenient way to represent various kinds of mathematical objects. Essentially, any graph is made up of two sets. One, a set of vertices, two, a set of edges. The edges may be directed or undirected. A single element of V is called a vertex and is usually represented pictorially by a dot with a label. Each edge in E is a set of two vertices from V, and is drawn as a line connecting the two vertices. Depending on the particular situation, restrictions are imposed on the type of edges we allow. For some problems, directed edges are applied, and for other problems, undirected edges are applied from one vertex to the other. So graph gave us many techniques and flexibility while defining and solving a real-life problem. To analyze the graph theory application, two problem areas are considered. One is the classical problem, and two is problems from application. The classical problems is defined with the help of the graph theory as connectivity, path, and flow, coloring problems, and the theoretical aspect of graph drawing. Whereas problems from application particularly emphasize experimental research and the implementation of the graph theory algorithms. In graph theory, graphs are not like where you have to plot some data on x-axis and y-axis. It is more like what you see in the figure on the right here. This graph have a bunch of nodes which are colored dots in the picture, and edges are lines that connect those dots. The main purpose is to go from one node to another using the minimum lines and find the shortest possible distance. These graphs have endless application in both math and computer science. Graph traversal algorithms is an algorithm that decides which is the shortest way to reach a destination. The graph is one nonlinear data structure. This graph can be represented as G instead of V and E. The letter G here represents graph, and V is vertices, and E is edges. The following graph in the picture here can be represented as shown in the following set. The graph has two types of traversal algorithms. These are called the breadth-first search and depth-first search. The breadth-first search, or BFS traversal, is an algorithm which is used to visit all of the nodes of a given graph. In this traversal algorithm, one node is selected and then all of the adjacent nodes are visited one by one. After completing all of the adjacent vertices, it moves further to check other vertices and checks its adjacent vertices again. And the depth-first search, or DFS, is a graph traversal algorithm. In this algorithm, one starting vertex is given, and when an adjacent vertex is found, it moves to that adjacent vertex first and tries to traverse in the same manner. Google Maps and graph theory. The entire premise of Google Maps is using a big giant graph with nodes and edges to figure out the fastest or the shortest way to travel. Let's consider this graph as an example. We can take each node to be a node in Google Maps, so it could be a city, intersection, or someone's house. And an edge to be the distance between two nodes, could be a road or a sidewalk. An edge could represent a road, sidewalk, or something similar. In the case of this graph, we as people can see that the shorter distance from node 3 to 1 is going from 3 to 4 to 5 to 1, and not from 3 to 2 to 1, because of how the values of the edge add up. So as you can see, 14 plus 12 plus 7 is less than 24 plus 22. This is just a small example. However, the great thing about it is that the significance or value of the edges could change, yet the algorithm itself would not change. So instead of representing distance, it would represent travel time by car.
So today I'm going to be showing you how graph theory is used in applications such as Google Maps, Apple Maps, Garmin, etc. So the way that it's used in society is that you can find communities in networks, linking or ordering hyperlinks in search engines, studying molecules and atoms in chemistry, DNA sequencing, and computer network security. And graph theory and probability make it possible to guarantee a reliable service. For example, we can find diversions when a particular connection is busy. Graphs also play an important role in transportation and navigation. So all flight, train, and subway networks form graphs, which can be used when creating efficient schedules. All roads and highways also form a large network, which can be used by navigation services like Google Maps when working out the shortest route between two given points. When we draw social media graphs, we also might see certain clusters of mutual friends who may have gone to the same school or live in the same city. And as stated before, graph theory doesn't really use distance as a method of measurement, but it uses time based on how long it'll take for you to get from point A to point B by car. And so for this following example, I am going to be using a weighted graph. Now I am going to illustrate how graph theory works in navigation. So to start, I'll draw 6 letters, A, B, C, D, E, and F. And now I'm going to connect the letters together. So A will connect to D, and A will also connect to B. D will connect to E, and B will connect to E. A will connect to E, and B will connect to C. C will connect to F, and then E will connect to F. Finally, B is going to connect to F. So now the letters represent nodes, and there are 6 of them: A, B, C, D, E, and F. The connecting lines between the letters are called edges, and there are 9 of them. Now we are going to take this map and abstract it to a graph. This is going to help us understand a little bit more about method mapping technology and how it helps calculate things. Okay, so here's our map we're going to demonstrate on. On the top we have A Avenue, B Avenue, C Avenue, and D Avenue. On the left-hand side, we have 1st Street, 2nd Street, 3rd Street, and 4th Street. Now, let's say we're at 4th Street and we want to get to the 1st Street and D Avenue intersection. So this is how mapping technology helps us think about this. We can also make assumptions about the map based on if the graph is directed or undirected. In this case, the graph is going to be directed. What this means is that directed graphs have direction. So for example, let's say that all of the streets are one-way. A Avenue is a one-way street going up. B Avenue is a one-way street going down. C Avenue is going to be a one-way street going down, and D Avenue is a one-way street going up. We're going to say 1st Street is a one-way going to the right. 2nd Street is a one-way street going to the left. 3rd Street is a one-way street going to the right. And 4th Street is also going to be a one-way street going to the right. And on this little cross street here, we're going to go up like this. On a directed graph, you don't really need to assume that everything is directed because you can have a graph with partial direction. In this case, we're just going to assume that everything is only a one-way street. So now we should think about why we would want to take one route instead of the other. This graph is going to be directed, but it's also going to be a weighted graph. So a weighted graph basically means that the edges, or like the intersections, are going to be labeled by numbers. Okay, so now we're going to label each of the intersections. We're going to say that this is going to be intersection A, B, C, D, E, F, G, H, I, J, K, L, and M. So where we want to start is at intersection K. And now we're going to label our nodes, and we're going to create a node for each of the intersections. So, as you can see, this is going to be node A, B, C, D, E, F, G, H, I, J, K, L, and M. And now we're going to indicate directions. So everything in this row is going to go to the right. Second street is going to go to the left. Third street is going to go to the right. And fourth street is also going to go to the right. And then we also know that A Avenue goes up, B Avenue goes down, C Avenue goes down, and D Avenue goes up. So now our graph has some direction, and remember we're at K, right? So we're going to get to D. In this case, you have a couple of options. You could either go all the way up and all the way to the right, or you could go all the way to the right and then go up. But in some cases, it's not that simple. So we're going to say that there's a cost in this graph. So for example, let's say that there's a cost going from one intersection to the other. And so basically, in this graph, the cost is that it takes a certain amount of time from one intersection to another. We're just going to say that it's going to take 3 units to get from K to L. It'll take 2 to get from K to I. It'll take 1 unit to get from I to E, and we're going to say 4 units from A to E. So there are a lot of reasons why the weights might differ. Let's say the distance is longer from one intersection to the other. The speed limit, might be different, or there could be construction or road work or something right here. There's construction happening, the weight would actually be pretty high, so it might be 10. And then there could just be normal traffic from A to B, so people are probably most likely just going to be rerouting from this construction over here. And this is going to have a weight of 8. But maybe this is going to have a weight of 3. 2. And then this is going to have a low weight. 2, 3, 4, 5, 4, 5, 6, and 5. So now we know that information is always being sent from mobile devices. And that means that mapping software is always going to get new data. So when there's a new traffic jam, the data is getting sent from mobile devices to their servers so that the traffic data can be used to calculate the quickest way from one place to the other, which does end up being pretty useful. So I'm just going to label the rest of the weights for this graph.
These are examples to show how graph theory works. And to summarize our presentation, we first started by explaining the history of navigation. Second, we talked about the evolution of navigation. Then we talked about modern navigation and how it's used today. Lastly, we explained the graph theory that is used in navigation and its relation with computer science. Again, graph theory has so many applications in computer science, and many problems of the real world can be represented by graph. With graph theory in navigation, it makes our traveling easier and saves some time for us.